So I am back in my PHPP, and let's take a look in this session at whether or not we think we'll be able to meet those passive cooling thermal comfort targets. So if you have been following along, hopefully you have a PHPP that looks something like the one here. You should be getting some good results for space heating, space cooling demand. All of our assemblies have been entered, all of our shading has been entered, our ventilation system has been entered. We finished up our domestic hot water system, etc., etc. So we have an awful lot built into our PHPP here, so we're getting some, I would say, reasonably accurate result values for things like overheating percentage and cooling energy consumption. And it's time to kind of start diving in here and seeing whether or not we feel like we need to add an active cooling system or not. So I'm on the verification worksheet page here, and the very first thing that I want to do is I want to come into my PHPP and I actually want to turn off mechanical cooling. So I'm in my verification worksheet. And if you remember, let me zoom in a little bit here. If you remember way back in the very beginning, of our filling out of the PHPP, I said that I was going to turn on active cooling in my project. So going all the way back to some of our very first videos, you saw me turn on mechanical cooling up here in this cell. For our purposes here for this video, what I want to do is actually turn that off. So I'm pretty confident, having done a lot of these buildings, that we're going to need active cooling with a building like this in a climate like New York State, which is where I've placed my building. But let's give the benefit of the doubt to the building. Let's say we want to move through in a sort of methodical way. Maybe we don't know the answer. Maybe we're not sure if we need mechanical cooling or not. So what I'm going to do is I'm going to come here and I'm going to turn off mechanical cooling by coming to this cell in the ventilation worksheet, or excuse me, verification worksheet, and switching it from an X to a blank input. And notice when I do that, some stuff down here changes. So what's happened just now in the PHPP is we've turned off all of the active cooling worksheets, so all of the worksheets associated with energy consumption due to cooling, air conditioning systems, and the like. And what we've done is we've told the PHPP, I want to try and meet thermal comfort during the summer period without any active cooling system, so using passive cooling only. And so when we do that, there's going to be two criteria that we want to keep in mind, that we want to assess when judging whether or not we can actually meet this threshold. And that's these two values right here. So we have a frequency of overheating percentage. So overheating defined as above 77 degrees Fahrenheit, 25 degrees Celsius. And a frequency of excess high humidity, so overly humid interior conditions, defined as above 0.012 pounds of moisture per pound of dry air. And notice here I'm getting a result of 34% overheating. So 34% of the time period is projected or predicted to be overheated above 77 degrees in my building, and an overly humid condition of 17%. So 17% of the time period above that humidity threshold. So my building, the way I've built it, is really hot and really humid. These numbers are not very good. So what should those numbers be? Well, if you see over here in the criteria section, notice that for the frequency of overheating, we have a target or an upper threshold of 10%. And for the frequency of excess high humidity, we have an upper threshold of 20%. Now, I think those numbers are far, far too high. So those are the certification limits. You can certify with values up to those numbers. If you want to keep your occupants happy, you should, in my estimation, be nowhere near those limits. Those limits are, I think, far too high for thermal comfort for most folks in North America. So unless you want to get a lot of complaints from your occupants, if you're building in North America, you should keep those numbers to much, much lower numbers. For instance, I would say that if you want to really do passive cooling, you should keep that frequency of overheating down to maybe 2 to 3%, and the high humidity down to maybe 5 to 10%, somewhere in that range. I think those would be good, reasonable numbers. And if you're above those, you should either have a hard conversation with your occupants about the level of comfort that you're going to be delivering, or you should consider active cooling. In any case, 34% is way above either our actual threshold or my recommended threshold. And 70% is very high for humidity as well. It's not above the certification threshold, but it is quite high. So what are we going to do about those numbers? What can we do to try and drop those numbers, try and drive those numbers down a little bit further? Well, as we talked about, there's really two strategies you want to undertake with passive cooling. So first of all, you want to try and reduce the amount of heat gain, and then you want to increase the amount of heat loss. So you want to reduce the amount of gain, the amount of sun and the amount of energy coming in, and then you want to use ventilation primarily to take heat out of the building. So let's start with the first one. Let's see what we can do to reduce the amount of heat gain. Well, the first thing that we talked about is that we can adjust some of the colors of the surfaces of our building and see if that reduces some of our heat gain. So the way that we could change the color of our building, change the absorptivity of the surfaces of our building, would be to come over here to the Areas worksheet. So if we shift gears and go to the Areas worksheet, and we remember the Areas worksheet, of course, from way back at the beginning of our PHPP. If I scroll up to the Areas input section here, we remember inputting all of these way back when. And if I scroll over to the right-hand side, let me do this. I'll freeze this so that we can keep these surface names. If I scroll over to the right-hand side, if you remember, we had a bunch of parameter inputs here that we sort of used some default values for way back when we were doing our surfaces. But maybe we want to be a little more careful now, and maybe we want to try to adjust some of these values. So for instance, we could come in and we could adjust things like the shading reduction factor, the exterior absorptivity, or the exterior emissivity. Now, let's take one of those off the list. Let's say this exterior emissivity just is what it is. Almost all typical construction materials are going to be somewhere in the neighborhood of 0.85 to 0.9. If we were using uncoated galvanized metal siding or something like that, maybe we could consider using a lower emissivity value, or not. Let's just say that we're using typical wood clapboard siding on our little house here. And so we're just going to use the exterior emissivity values of 0.85. So we're not going to adjust those at all. So let's just say those are what they are. There's nothing we can do to modify those. Perhaps we could consider using a low emissivity roofing material if we wanted to say to the client, well, one way that we could potentially reduce your heating energy would be to use a high reflectivity metal roofing or something. That might be a strategy, but let's say for our purposes, we're just going to leave those set to the normal values. Now, what about these other two? Well, shading reduction factor is a number between 0 and 1, 1 meaning fully exposed to the sun, 0 meaning fully shaded. And if we bring up our site plan, let me go grab our site plan drawing here, which of course we've looked at many times. We know that we don't have a lot of shading on this site. There's no buildings nearby. There is a little garage here on the north side, but that doesn't amount to a hill of beans. There's no plantings. There's very little shading around the building here. So I don't think there's really much we can do in terms of shading. So I think maybe 0.7 is even maybe a little bit low given the exposure of the building. The only one here that maybe we have any control over is this guy here, the exterior absorptivity. And the absorptivity is, so you can think of it as a proxy for color. If we hover our mouse over the little tooltip here, we get some helpful hints where the PHPP says, well, look, if you did a bright white paint, maybe you could make this value as low as 0.4. Maybe if you have some like special, high solar reflectance value, it could be down as low as 0.1 or 0.2. If it's something like a black color, maybe more like 0.95. And this is obviously going to affect our cooling in some degree. The darker colors are going to absorb more solar radiation, are going to heat up further, are going to drive more thermal energy into the building. So we're at 0.6, which is kind of a medium value. Let's say that we're going to paint our little cabin or whatever you want to call this farmhouse here bright white. Maybe we're going to do that bright white farmhouse thing. Whoops. So let's set these to 0.4, and I'll just go ahead and set that all the way down. I guess it doesn't matter. Setting the slab on grade doesn't matter. That's fully shaded, and setting the ceiling also doesn't matter. That's fully shaded as well. So these guys don't matter. We could set these to anything. So it's really just the walls here that matter. So let's say that we set those to 0.4 though. So let's set those to a brighter color, and then let's see if that did anything for our overheating. Not a whit. Okay, so with our 40 walls, such highly insulated walls, going from point 0.6 to point 0.4 doesn't really amount to much change at all. All right, so that didn't really help us at all. In some other circumstances, maybe it would, but in this case, it did not do anything for us. So that didn't really change our value there at all. So what else could we do? Well, we said one of the other things that you can do is you can use really efficient lighting and appliances to reduce your internal heat gains. Well, okay, so we looked at electricity way back when. Remember, we have this electricity worksheet where we can designate all of our equipment and our appliances here. So maybe one of the things we might want to do is get rid of our Bitcoining nonsense. Maybe we would say, you know what, let's turn these off. Let's get these out of the building here. Let's turn these off. We certainly don't need an elevator in our two-story house. And our exterior lighting, we can leave that on. It doesn't matter. Remember this column here is it inside or outside of the envelope? Meaning, does it affect your internal gains or not? So I just turned these ridiculous ones off. But really, this is, well, let's see, did that do anything for us? Come all the way back to our verification here. No, nothing. So that didn't affect that at all. So that doesn't do anything there. And let's see, we could adjust some of the other values here, but I happen to know that it's not actually going to do anything. So if we were to go, so we could start monkeying around with all of this, but really, if we were to go back to our verification worksheet, remember that way back when, we said that we should use standard values for all of our internal heat gains. So the way that we're kind of monkeying around with this isn't going to affect things very much. We're just using the standard values here. So there's really not much we can do on the internal gain side. Changing the color didn't really do very much for us. There's not too many other levers that we have in terms of the heat gain, excepting shading. We'll come back and talk about shading in a future video, so I want to take our time and talk about that later. But let's say that we've kind of exhausted our efforts here in terms of reducing heat gain. Again, we'll come back and talk about shading at a later date. But let's say that we want to increase our ventilation losses. So let's turn our attention to the other side of the coin and let's talk about increasing ventilation loss. Let's talk about summer ventilation. So let's see if we can take this 34 number down a little bit further. So the place where we're going to adjust our summertime ventilation is, of course, going to be this summer vent worksheet. So we have a whole worksheet here dedicated to summer ventilation. We have already looked at this worksheet a little bit when we were setting up the basic ventilation for our summertime strategy. Remember, we want to turn on the ERV by making sure that we enter a value here, and then we want to put in a nominal amount of window ventilation that gets us up to that 150% threshold. So this is the minimum ventilation that we would want in our project. But of course, we probably want a little bit more ventilation for cooling purposes. So it's possible that adding more ventilation might help us drive this 34% number down. Notice I can get a little quick readout up here of my frequency of overheating up at the top of the worksheet here. So I'm at 34% right now. I can also see it right here at 34%. So we want to get that number a little bit lower. All right, well, so we said before that this was just a real simple number, and all I did here was actually just take the basic ventilation and multiply it by 0.5. So I said, just take this number and multiply it by 0.5. These numbers then get added together to give us a total ventilation flow rate, 150% of the wintertime. But this is not based on anything. Like this was just a nominal amount. So let's actually figure out how much summer ventilation can we really get through our windows. And the way that we're going to calculate that for our purposes is over here on the right-hand side. We have these little calculators that help us calculate window air change rates. Now, if you don't like this and you want to go off and do a computational fluid dynamics model of the windows on your project, you by all means. I'm not going to do that. I'm going to use this simplified little numerical calculator here to help me estimate, probably conservatively, but help me estimate the amount of air exchange that I can get through operable windows. And we'll take a look at this one at a time. Notice here, first of all, that I'm asked to input a bunch of information, and I have up to 5 or 6 of these banks of windows. And the reason we do that is, notice here I've got window group 1 and 2. So I can model opposing windows by entering data in these two sections here. So I can model chunks or sort of banks or sets of windows. And then at the bottom here, notice I get a resultant air exchange rate, and then we get a total air exchange rate for all the windows in the project. Well, okay, so let's go through this sort of one piece at a time. Let me zoom in a little bit here so that we can kind of see this a little better, and we'll enter some information here one bit at a time. All right, so let's say we want to model a first bank of windows. So let me do this. Let me bring up my floor plan here, and let's model some operable windows. Let's see what's a realistic assessment for air exchange through the windows as designed in this project. So let's start with this. Let's see. Let's start with, let's just start on the north. We always start on the north with everything, right? With all of our data input. So let's start on the north. What about these two windows here? Which of these are operable if I go down to the elevation? Okay, so it looks like they're both tilt-turn windows, if I'm reading the operation correctly on the drawing here. So these are tilt-turn windows in north window 1 and north window 2. So we've got two windows that are both 3'4" by 3'4". Okay, so let's go back to our PHPP here. So let's say these are the north side. We'll call these north side windows. I guess I don't need to say window. We're always talking about windows in this. All right, so we give them a description. And then the next thing we're asked to input is, what's the duration? So during the day, on average, over the course of the year, how long are these windows open? Realistically, are you in the kind of place where you leave the windows wide open all day long? Or do you close them during the day when you leave, if you go off to work or something like that? Or is somebody always around and you're able to keep the windows open all the time? And that's just a decision you have to make as a designer. You know, what kind of building are you building, and how conservative do you want to be with this type of modeling? I'm going to say that these windows are going to be open. Let's say a building like this, let's say that these tilt-turn windows are actually open 12 hours a day. So these windows are actually left in the tilt condition, meaning they tilt in. So they're not wide open. So from a security standpoint, they're kind of, they're closed enough. But they are tilted in to allow for ventilation. So I'm going to say they're open 12 hours a day. So all day long during the summertime. Okay, so now the next thing we have to input here are a couple of boundary condition values. And we're supposed to input a temperature differential between inside and outside, and then a wind velocity. So what do I put in for those? Well, if I hover my tooltip over here, I'll see a little hint. The hint says, well, for typical summer values for whole day, you should put in 4 degrees Fahrenheit. That is, sad to say, a typo. I know it's a typo because if you were to come down here and you were to go right click and unhide, and we were to unhide the summer ventilation SI worksheet, if I was to unhide the summer ventilation SI worksheet, and I was to come to the same place on my summer ventilation, and I was to zoom in on temperature difference for the daytime, and I was to hover my mouse over it, notice that the tooltip here says the typical ventilation delta T should be 4 degrees Kelvin. Well, 4 degrees Kelvin is not 4 degrees Fahrenheit. So unfortunately, this is just a typo. So in fact, we're supposed to enter something like 7.2 degrees Fahrenheit. Let's just double check that. Yes, that gives me, so 7.2 degrees Fahrenheit gives me 4 degrees Kelvin, which is what we want to input here. So unfortunately, typo there. Don't get confused by that. Input 7.2, something like that. That will give you the right value over in the SI worksheets. Now the wind velocity is correct. So this tells us to put in 2.2 miles per hour, which resolves to, I think, 1 meter per second. We'll just double check that by going to the SI worksheet. Yes, 1 meter per second there. Yeah, 1 meter per second. All right, fine. So those are input there. So those are reasonable values. I don't know how to determine those values. If you don't like those numbers, I don't know what to tell you. I don't know where they got these numbers from. I just take them from the little tool tips here. All right, so the next bit down here asks us to input the size of the windows. So we have to input a couple of things about the size of the windows. So let's go back to our elevation here. So I'm modeling these two, north window 1 and 2, and these are 3'4" by 3'4". So pull this one off to the side so we can see it there. All right, so I've got two windows. And what do we want to put? We want to say that the width is equals 3 foot plus 4/12 of a foot. So that's my width. And then I want to put in this clear height, and clear height's the same thing, so equals 3 plus 4/12 of a foot. And there we go. So I've input my width and my height. Notice I'm still not getting a result down here for my resultant air changes. So I need to input two more things. First of all, is it a tilting window, yes or no? If it is a tilting window, go ahead and mark it with an X. So these are tilting windows. I'm saying these are going to vent the building in tilt operation. And the next thing it's asking me is the opening width. Now, what does it mean by opening width? Well, what it wants to know is what's the minimum dimension when this window is open that air can flow through. What's the smallest dimension? What's the tightest, the most constricting dimension there when you open the window? Now, for a casement window, if this is in casement operation, if we were sort of swinging this open in casement mode, the opening width would be the width of the window minus the thickness of the frame on both sides. However, in tilt operation, that opening width is going to be a little bit different. So I've prepared a little diagram here. Let me pull that up, a sort of section diagram. Well, let's do this. If we come down to our section here, just to make it super clear, we're talking about a window like this one here, right? So if we have a window like this, it's going to tilt in. It's going to tilt in at the top, and a tilt window is going to have a different opening width. So let me pull up the little diagram here. And the only way to figure this out is to get your hands on the actual CAD profile for the windows that you're working on, figure out where the hinge position is, and then draw in the open sash of the window and measure the dimension relative to your wall. Depending on the thickness of your wall, the way you trimmed out the window, the position of the window, how the window opens, how high and tall the window is, will affect all of these things. So for our purposes here, you can see that we've got the window represented in the wall, exterior is on the left, interior is on the right, and we can show or are showing a sort of schematic level assessment of the open window there, the tilting window. You know, these tilt windows they tilt in, 15, 20 degrees, something like that. And given the thickness of our wall here, what that means is that the constriction point, in our case, is maybe somewhere around 3 inches, 75 millimeters. And again, the only way you would know this is if you draw it out. You have to really draw it because it depends on where the hinge position is in the frame. So you have to really draw these things out. It's the only way to really know. So for our purposes, though, let's say 3 inches will be our opening width number. So let me pull that back off to the side, pull this off, come back over here. So let's say our opening width for our tilting windows is going to be 3 inches. Ooh, I think I've made a mistake. Notice here, the PHPP was asking me for inch input here for the width and the height, so I apologize about that. So this is easier. Let me go back and fix that. 36 plus 4 and equals 36 plus 4. Sorry about that. I was just made a lazy assumption that it wanted feet. It wanted inches for these. And so at 3 inches there, our two north side windows are responsible for 0.09 air changes per hour. How does that stack up? Let's come back over here to our total. Well, in total, we want 0.21. Well, that's interesting. So let me bring back our drawing set here. Go back to our floor plan. So I said at a minimum, I want 0.21. And these two windows alone in tilt operation can supply about half of that. But we have a lot more windows than just these two, don't we? Well, so we could go in and we could start to model out these other ones and see what the impact of those would be. So the other thing that we might want to do here, let me go back to the PHPP for a second. The other thing that we might want to do before we move on to the other windows is just finish up this set. Notice here we have another section where we're able to enter opposing windows for cross ventilation purposes. So if we have windows which are opposite to this first bank, we can also enter a height difference, and then that will increase the air exchange rate here significantly. Now, for this case, these two windows, I'm going to say these don't have an opposing window. You could maybe make the argument that like this window over here, but not really. It has to go through. It's assuming this door is open. It's really around the corner here. I'm going to say that these windows do not have a sort of cross ventilation, like an opposite, assuming that we don't leave this door open all day, every day. If we did, if we had good robust screens or something on this, if we had a screen porch here, maybe we could leave this door open, and then obviously we would get a tremendous amount of air exchange across the main space here. But we don't, and so I'm going to say we have to assume that this door is closed during the summertime. Might be a good reason to build out a nice little screen porch or something here. In any event, so let's leave that alone. Let's do another space. Let's do it the den, because the den, we maybe could argue that we have opposing banks of windows here. So we've got 1, 2, 3, 4 windows. Let's just remember, I don't remember which of these are operable, so let's just go down. Okay, the east windows. So both of the east windows are operable. Oh, and both of the south windows are operable. Okay, good. So those are all operable windows. And so let's model these two and then these two in the den. So I'll come back to my PHPP and we'll come in here and we'll say these will be, I'm going to model a new bank of windows here. And I'll say these will be the den windows. And how long are the den windows open? Let's say these are also open 12 hours a day. That might be a bit aggressive. That might be a bit ambitious, but let's just say for purposes of argument they are. We'll use the same temperature differential and the same wind speed for all of these. And then the next thing we need to do is we need to model in the windows. So I'm going to model these two as bank 1, and then these two as, or set 1, and then these two as set 2. So I'll model 2 windows for set 1, or group 1, and 2 windows for group 2. Now let's go back to our elevation and take a look at the sizes. So these are 2.7 wide and 4.9 tall for set 1. So the width there, what did I say, equals 24 plus 7. And the height there, I already forgot, 4'9" equals 4 foot, or 48 plus 9. These are tilt windows, and let's say that they have the same 3-inch opening width. And then window 2, so that's group 1, and then group 2 will be these guys over here, and they are the same, 2'7" wide, 4'9" tall. So I'll do the same thing. I'll just say 31 and 57. These are also tilting windows, and these will also have the same 3 for an opening width. And the difference in window height, I don't think we have any difference in window height. It looks like they are at exactly the same elevation, so I'm going to say there is no difference in height. But notice those windows are now going to give us 0.36 ACH. So now we're already, so 0.36 plus 0.09, now we're already well above that 0.21. We've like doubled that just with those 6 windows. And we could continue to go through and add in the rest of our windows here to see what kind of a total we might get. Let's go ahead and do the rest of our first floor windows just for completeness here. So let's go ahead and we'll add the bathroom in, the bathroom window there, and then we'll do the entry and the mechanical room. So let's see, the bathroom window there was 2.7 by 2.7. So we'll call this bath. Floor 1, let's say it's open 12, 7.2. Remember, 12 is maybe a little bit aggressive, but you know, 31. That was 31 by 31. It was a tilt window, and it's going to be open 3 inches. That's your opening width there. And then we'll call these. What else do we have? We've got this guy here. 2.7 by 4.9, that's the mechanical, and then we've got another one here, 2.7 by 4.9. So I'll just call these floor 1 windows because they're both the same. We'll say 7.2. Whoops, I should have done. Oh, that might just be a. Let me correct that. That's just a display thing with Excel. 2 windows. We said they're 31 inches wide by 57 inches tall. They are tilt and they are open 3. All right, so there's my first floor window. So I've got all my first floor windows modeled in. Now I could go in and model my second floor windows as well. Second floor windows, what do we have? Well, it's going to be a little bit tricky. I guess let's try and do this. Let's say we don't really have any, well, let's do this. Let's model the bedroom and let's model the two bedrooms as opposing sets of windows. So let's model bedroom 201 first. So let's say bedroom 201. Bedroom 201. And let's say these are open 12 hours a day and 2.2. And okay, so bedroom 1. So we've got a window here and a window here. So let's do the south window first. So we've got this little guy, so 27 by 27. So we've got one of those at 31 by 31. It is a tilt window, so 3-inch opening width. And then this one is opposed by this guy here, this west window. So this is 2.7 by 4'9". So here we'll say we've got one. It is 2.7 wide by 4'9" tall. It is a tilt, and it has got a 3-inch opening width there. And okay, so there's 0.15. And then let's do the other one. Let's do bedroom 202. Is that the number? Already forgotten. Let me go back to the floor plan here. Bedroom 204, excuse me, bedroom 204. So we'll have two windows here and two windows there. So 204. And 204, we'll say 12, 7.2, 2.2. We fix that. Okay, so we've got, let's do the south windows first. So we'll use south windows first. And so these south windows are both 2.7 by 2.7. They are both tilt turn. So we've got two windows, 2.7 by 2.7, both threes. And those are going to oppose windows on the east side. So here's our two east side. Notice the one in the middle is fixed, so we are not going to include this window in our set. So this doesn't count. This is a fixed window. We've only got these two side windows. These are both 2.7 wide by 4'9" tall. So I've got two windows, 2'7" wide by 4'9" tall, tilting, 3. And there we go. Now we could model out the last remaining windows there. We could add these little guys in, but this is how we would go through and model these guys for the daytime. And notice our total here, 1 ACH, significantly higher than the 0.2 that we were estimating and using as a basic value. So let's now set this as our daytime air exchange. So if I come back over here to the left, notice this is still set to 0.2. This little calculator on the right-hand side is just that. It's just a calculator. The data that it calculates doesn't go anywhere by default. So we have to take that number and input that number here. So I could either come in and just type in 1.05. That would be perfectly fine. Or I could make a link. I could come and select the cell. I could type equals. Then I could come over here. And I could enter this value. And notice I get 1.05. So significantly higher than that basic ventilation rate. We're much higher than the 150%, which is great. So we're going to have additional air exchange. And let's see what that did to our overheating. If I come up here to the top, there, that's pretty good. We went from 34% down to 29%. So that's pretty good. We took a big bite out of our overheating percentage. So he said, the PHPP says, okay, that's great. If you can do that, if you can keep those windows open like that, then that's going to release a bunch of heat that's built up in the building, and you can decrease the amount of overheating. So that's fantastic. But 29% is still pretty high. So let's see, is there anything else we can do to improve that number here? Well, remember, this is daytime window ventilation. We have a whole nother entry down at the bottom here for nighttime window ventilation. And currently, we are telling the PHPP that at night, we close all the windows on this building, which of course is probably not realistic. The nighttime, especially in the shoulder seasons, can be one of the best times to open up all the windows and let that excess heat that's built up over the day void out of the building. So what's the right number to put in here? Well, the PHPP has included a handy little calculator over on the right-hand side for just that purpose. So we have another calculator. This looks very similar, but notice here it's labeled as nighttime cooling as opposed to our daytime cooling one up here. So, okay, so what do we want to input here? Well, let's see. We want to model the same banks of windows. So I'm going to do this. I'm going to grab these guys. I'm going to say copy. I'm going to come down here and I'm going to paste those in. I'm going to say paste special and paste values. I like to do that so that we preserve the formatting. Now, the other thing that we are asked to input here is a reduction factor. So we have the opportunity here to input an additional reduction factor, some number between 0 and 1, which allows us to reduce the amount of air exchange through the windows. The assumption, or the sort of basis of the calculation that the PHPP is about to do, is that this whole set of windows is going to be open for 12 hours a day. And so if that's not true, if those are only open for 6 hours a day, you could also input a reduction factor in order to account for the fact that these are only open a few hours a night or something like that, if you don't leave them open for the entire night period. But by default, the PHPP is going to assume everything you put in here is going to be functioning for 12 hours a day. And so if that's not true, you can use this reduction factor to adjust that. If we're going to leave it blank for now. Let's just say we're not going to have any additional reduction factor. Go ahead and calculate this for the nighttime period, that nighttime 12 hours per day. And we're asked to input basically all the same information here. Notice that we have specified values for temperature and wind velocity here, so we don't get to put those in, but fine. So I'm just going to come up here and I'm going to grab this, say copy, come down here and I will say paste special values so that we keep the formatting. And I'll do the same thing with my lower bank here. I'll say copy, and I'll come down here and I'll say paste special values. And notice I'm still getting all zeros here, and that is, I forgot, we have to, if we don't want to put in any reduction, we have to put in 100. So we have to put in 100%, 100% meaning no reduction, no additional reduction in air exchange. So 100% maximum air exchange. And when we do that, notice down here we get an air exchange, a total air exchange for the nighttime period of 0.73. And just like before, that number doesn't go anywhere by default unless you have specifically set up that link. So notice here that this is linked over to that value, 0.73, so that's going to flow through into our nighttime ventilation. So we get our what are you doing? 0.73. There we go. So let's see what that did. There we go. So there's our nighttime ventilation. We could add in additional mechanical ventilation if we had an additional fan or something, a whole house fan or something to flush the building. But let's see how that did. Just a 0.75 nighttime ventilation. Let's see what that did. Now we're talking. So that knocked us down to 20% frequency of overheating. So we went from 34% overheated down to 19% overheated. That's a pretty significant reduction by increasing the amount of ventilation in the building. Now we've pretty well maxed out the ventilation in the building though, unless we wanted to add more windows or we wanted to make some claim about the windows being in casement operation or something. There's not a lot else we can do. We've sort of built in all of the ventilation that we could here, and we're still at 19%. So 19% was a lot better than 34%, but in my estimation, still far too high. So I think we should break this video here. We've gone on for quite a long time in this video, so it's been a long one. When we come back in the next video, we'll turn our attention to the shading situation. So the other big wildcard here, or the other big influence on this overheating percentage, is obviously going to be the shading and the solar gain. So when we come back, we'll take a few minutes and talk about solar gain and shading and see if we can't do anything to improve that situation. And then, of course, we'll make a decision about whether or not we think we need active cooling in our building.